Why do we exist? At the heart of this question reveals the most profound quest of human enterprise. Everything from the minuscule electron to the colossal galaxies is made out of matter. But for some reason unknown, matter's evil twin antimatter is nowhere to be found. Theoretically speaking, every matter particle has its unique antiparticle pair. Antiparticle has the same mass as its matter companion, but is opposite in charge. When both matter and antimatter interact, they annihilate, leaving behind pure energy. The Big Bang should have created matter and antimatter in equal amounts, but the matter seems to have dominated the atom.
Physicists are so sure that antimatter is nowhere to be found except for a few nuclear decays and high-energy collision in particle accelerators.
Because if some antimatter galaxies were to exist, then they would have emitted
radiation and energy on interaction with matter stellar corpses.
Before probing into many abstract theories and hypotheses, let's make sure we are on the same page. By the first half of the 20th century, whole of physics was in turmoil. Theoretical physics was led in the 1930s and 1940s by Schrödinger, Dyson, Feynman, Nambo, Julian Swenger, and Wolfgang Pauli.
All of them were struggling relentlessly to come up with a mathematical formalism that encapsulates the discoveries of that day.
Schrödinger's equation was turned out to be shallow in its scope, and was approximate only if one does not probe deeper into the microscopic frenzy, but certainly fails down if one does.
This was because Schrödinger ignored a central piece of modern physics, special relativity.
In 1928, English physicist Paul Dirac wrote down an equation marrying special relativity with quantum mechanics. But such a relativistic equation posed an unseen problem, like a simple quadratic equation. Solving a Dirac equation for the energy of electron reveals a startling fact: negative and positive roots for energy. But classical physics, common sense, dictates that energy must have only positive value. But dears, it's
quantum mechanics.
Paul Dirac went one step further and interpreted that for every particle, there exists an antiparticle counterpart and occupies negative energy, so that a matter electron would not descend the infinite negative energy potential and emit an infinite amount of radiation. Why matter electron does not descend? Pauli's exclusion principle? Okay, was that this theory is experimentally proven, so would have dawned in your mind.
I should say many times.
4 years immediately after the discovery, Carl Anderson in 1934 proved the existence of positron following the lines of Dirac's theory. But Dirac theory did not treat positron, or for that matter any antimatter particles, as real,
but as a whole indirect ocean of electrons. So Dirac's whole theory is not the end of the story.
With developments in quantum field theory, a comprehensive explanation was given to antimatter as a negative curvature of the geometry of field. Positron is a localized negative curvature of electron field. It's quantum because there is still uncertainty and probability and stuff. It's field because it incorporates the classical knowledge of force field from Maxwell's electromagnetism. According to the Standard Model, photons are the smallest constituent of the electromagnetic field. The Standard Model instructs us not to think of these force mediators as having internal structures so truly elementary as 3 families of matter particles: electron, tau, and muon. Photons, gluons, and gauge bosons provide a microscopic mechanism for the transmission of forces. So when one electron repels another electron, you can roughly think in terms of cloud or mist of electric essence interacting with each other. Or more precisely, electromagnetic field can be thought of as a swarm of photons, and shooting of photons among electrons can bring about repulsive interactions. The weak force was not well understood until 1967, when Abdul Samad and Stephen Weinberg's great insight unified weak force with electromagnetism. which had the same dramatic impact and grandiose as Maxwell unified electric field with magnetism 150 years ago.
Weak force diminishes vanishingly almost in subatomic distances. On the other hand, electromagnetism had macroscopic presences in
X-ray technology and radio transmission. They came up with 3 messenger particles of spin 1 vector bosons, which had a mass of 100 giga-electron-volt. In essence, their theory showed that at high enough energy, at energy of order more than 100 GeV, weak force field dissolves into electromagnetic field. Therefore, Steven Weinberg, Abdul Samat's theory showed this property of spontaneous symmetry breaking. What appears to be a number of particles at high enough energy dissolves to particles of one type. So this means at energy levels more than 100 GeV, photons behave the same way as 3 vector bosons. But the particle accelerators of 1960s were not able to reach the epitome of 100 GeV, so scientists will have to wait till 1983. But some of the low-energy consequences were verified experimentally as early as 1979. The success of electroweak unification led to grand unified theory. GUT. The name is personally to me grandiose and an explicit exaggeration, since it does not include gravitational interaction, which unifies electroweak force with strong force. The strong force has a peculiar property of asymptomatic freedom. That is, at high enough energy its energy content reduces, whereas electroweak force is not asymptomatically free. So at a higher energy level, it gets stronger. So at some grand unification energy, these 3 aspects of forces will have same strength, and thus be sides of the same coin. Not just that, GUT predicts that all the matter particle of 1/2 spin would be essentially same. Another essential prediction of the GUT is the subject of this discussion. According to the GUT, protons at this high enough energy could decay into lighter particles, like anti-electron, and so our very existence can be traced to the reverse process of decay of antiquarks to quarks. In the beginning of the universe, the cosmos was hot enough to allow such transformations to happen. But again arises an implicit question. If the odds of quarks decaying into antiquark is the same as antiquarks to quarks, then why there are so many quarks than anti-quarks? This was because laws of nature of the early cosmos were different than that of the present cosmos. Some unknown entity intervening in this process in the early universe could have caused these oscillating particles to decay as matter more often than they decayed as antimatter. Before 1956, people that the laws of physics were isotropic.
For that matter, both particles and antiparticles were subject to be symmetric on 3 grounds: charge, parity, and time.
But antimatter seems to have violated CP symmetry. Asymmetry in the matter-antimatter ratio may have been produced by the occurrence of CP violation in the first seconds after the Big Bang. Some scientists think that it could have been the Higgs mechanism that could have intervened in this process of oscillation. Higgs field is thought to pervade all space and provide elementary particles its characteristic mass. If the Higgs field started off with a very high value in the early universe and decreased to its current lower value over time,
it might have briefly differentiated the masses of particles from their antiparticles along the way, an anomaly,
because antimatter today is characterized by having the same mass as its matter counterpart. This difference in mass, in turn, could have made matter particles more likely to form than antimatter in the cosmos' early days, producing the excess of matter we see today. Kari Enquist of the University of Helsinki, on being asked this matter, remarked,
"There is a very high probability for the Higgs field to have a high initial value after inflation."
Whatever could have been the reason, physicists at CERN can hint at the tantalizing results by analyzing the properties of matter and antimatter by studying their properties created in high energy head-on collision. For more information, please visit our site. If you like this video, consider subscribing to the channel. Thank you.